All right. So today we move on to chapter 5, joining and assembly process. Let me get my pointer up. All right. So basically the overview, okay, for this chapter, we have the overview of the welding process, all right, an introduction to what the welding process will be like. And then we have the few listed welding process amongst the many, all right. Here we have resistant welding, oxy-fuel welding, and many others you will come across. Then we will discuss the welding quality, weldability, and what are the design considerations in welding, okay? And then next week, Dr. Shariman will move to brazing and soldering, mechanical fasteners, adhesive bondings, and robot applications, all right, in welding. So the overview of the welding process itself, okay? So we have what we call number 1, all right, fusion welding, okay? So it is basically a coalescence, okay, which is accomplished by melting the two parts to be joined, all right? In some cases, we add filler metal to the joint, okay? So the examples that comes under this will be like arc welding, resistance, spot welding, oxy-fuel welding, etc. And then we have number 2, all right, which is the solid state welding, all right, whereby heat and or, so it doesn't necessarily have to be both, pressure, they are used to achieve coalescence, but no melting of base metal occurs and no filler metal is added, all right? So we should be able to distinguish between fusion welding and solid state, all right? So in fusion, there is filler metal, all right, which is added, and the base metal does melt actually, all right? And in solid state, the coalescence is achieved without the filler metal and no melting of the base metal, all right? So the examples are like forge welding, diffusion welding, friction welding, etc., which we will come across. So here the welding is classified into different groups. Well, this is the general grouping, all right? Now we come into the methodological grouping, okay, of what we use, all right, to perform these welding processes. Hence, we have arc welding, okay, where we use different types of arcs. So we have metal inert gas, which is called MIG welding, tungsten inert gas, then plasma arc welding, submerged arc welding. So basically, it's the usage of arc, okay. And then we have gas welding, where you use different types of gas like oxyethylene, ethylene, hydrogen, all right. Then we have resistance welding, all right, where we have butt, spot, seam, okay. And then we have thermite welding, where we melt the material to create the weld. Solid state, okay, so early on the description of solid state is there's no filler metal and the base metal does not melt. So we have friction, ultrasonic, diffusion, explosive. And then we have more contemporary welding procedures like electron beam and laser, okay, and other related processes, okay, like we don't weld, but we use arc, all right, the similar arcs over here to do cutting, all right, so this kind of arcs for cutting, and then hard facing, brazing, soldering, okay, so these are the classifications in general, okay. So moving on to arc welding, right, it's a fusion welding process in which coalescence of the metal is achieved by heat from an electric arc, okay, between an electrode and the work. So the electric energy from the arc produces this high range temperature, okay, 5,500 Celsius, all right, hot enough to melt any metal. Most arc welding processes add filler metal to increase volume and strength of the weld joint, basically. So when you're melting something away, you can create porosity, gaps, and everything, so the filler metal will fill in. So what's an electric arc? An electric arc is a discharge of electric current across a gap, all right, in a circuit. So when you have a gap, the discharge of the current, all right, appears, all right, in the circuit. It is sustained by an ionized column of gas, which we call plasma, all right, through which the current flows. To initiate the arc in arc welding, the electrode is brought into contact with the work and then quickly separated from it by a short distance. Okay, so we have the arc welding over here. Just a minute. So a pool of molten metal, all right, is formed near the electrode tip. And as electrode is moved along the joint, the molten weld pool solidifies in its wake. So basically you have the arc and then you have the pool of molten metal. And as you move, the pool of molten metal solidifies. Sometimes the presence of filler will be there, all right? Sometimes it is not. So the manual arc welding and arc time, all right? The problems with the manual welding is the weld joint quality because, subjected to manual holding. So, there is no consistency, all right, in our movement process. Thickness, many other things, all right, will affect the weld joint. And the productivity itself, because as I said, it is manual, so it's reliant on human labor. The arc time is formulated, all right, basically the time the arc is on divided by the hours of work. So two basic types of arc welding electrodes. So we have the consumable, whereby when you use this electrode, the electrode itself is the filler material, right? Filler metal, right, which is consumed during the process. And then we have the non-consumable. Okay, the filler metal must be added separately to form the welding. So consumable electrodes, the forms, we have welding rods, all right, or we call them welding sticks. They are about 9 to 8 inches or 3 to 8 inch or less in diameter, and you need to change them frequently. Welding wire can be continuously fed from spools with long lengths of wire, avoiding frequent interruption. So welding wire is also a consumable electrode. In both rod and wire forms, electrode is consumed by arc and added to a weld joint as a filler metal. Non-consumable electrodes, just a minute, just give me a second. All right. So non-consumable electrodes, right? So they are made out of tungsten, okay, which resists the melting process. And it gradually depletes during the welding, okay? So it works based on the principle of vaporization. Any filler metal must be supplied by a separate wire fed into the weld pool. So those are the do's, right, in non-consumable electrode. And then we have the shielding arc, all right? At high temperatures in arc welding, metals are chemically reactive to oxygen, nitrogen, and hydrogen in the air. So the mechanical properties of joint can be degraded when we have this kind of reactions taking place, okay? So to protect the operation, we need a shield, all right, from the surrounding air that comes about. So the arc shielding is accomplished by shielding gases like, okay, inert gases like argon, helium, and then non-inert like carbon dioxide, and we use flux. So what is flux? It's a substance that prevents the formation of oxides and other contaminants in welding, all right? Or dissolves them and facilitates the removal. So it provides a protective atmosphere, it stabilizes the arc, and it reduces the spattering. When you have welding, you have a lot of arc spatter, so the flux will reduce it. So various flux application methods. You can pour granular flux onto welding operation, as you will see in one of the welding processes later. Then you have stick electrode coated with a flux metal. So if you have an electrode inside, all right, it's coated outside with a flux metal, okay? That melts during the welding to cover the operation. So basically, it's like a coverage. And then you have tubular electrodes in which flux is contained in the core and released as electrode is consumed. So what is the power source in arc welding? All right, we have the DC versus AC. So AC machines are less expensive to purchase and operate, but generally restricted to ferrous metals. All right. Direct current equipment can be used on all metals and is generally noted for better arc control. So this is more of a preference, DC. So here, the consumable electrode processes, okay, we have shielded metal arc welding, gas metal arc welding, flux core, electrogas, submerged arc welding. So these are the consumable process, of which now we are coming to the first one, which is the shielded metal arc welding, SMAW. So it uses a consumable electrode consisting of a filler metal rod coated with chemicals that provide flux and shielding. Okay, so sometimes it's called stick welding because we have the electrode, right? It's called stick. Okay, the power supply, connecting cables, and electrode holder available usually amounts up to a few $1,000s. So it is not a cheap process. Okay, So this is the schematic diagram of the weld which travels in this direction. Okay, so you have your protective gas from the electrode, and you have your consumable electrode, all right, which is consumed, all right, as the arc is produced. And you have an electrode coating. Okay, so this is the solidified metal, all right, which is forming across the movement. You have your base metal and you have your molten metal over here. So the welding stick in SMAL, all right, composition of filler metal, right, is usually close to the base metal naturally, because we don't want something completely different which creates a reaction. The coating, powdered cellulose, all right, over here, the coating of the protective gas from electrode coating. Okay, sorry, the protective gas is created, all right, to protect the electrode coating. Okay, so the coating, powdered cellulose mixed with oxides and carbonates, and they are held together by a silicate binder. So the welding stick is clamped in an electrode holder connected to the power source. Okay, and the electrode holder is also protected by the coating. The disadvantage of this, sticks must be periodically changed naturally, and high current levels may melt coating prematurely. Okay.
What is stick welding? Stick welding is an electric arc welding process that uses rod-shaped metal electrodes that are covered with a flux material. The American Welding Society calls this process shielded metal arc welding, or SMAW. You may also hear this process called manual metal arc welding, or MMA welding. Some people refer to this process simply as arc welding, but shielded metal arc welding, or stick welding, is just one of many types of arc welding. In stick welding, an electric current flows through a metal electrode or stick. An arc forms between the end of this electrode and the workpiece. The arc melts both the metal in the rod and the metal in the pieces to be joined. The metal from the electrode is ejected into a molten weld pool and mixes or coalesces with the workpiece. The metal in the workpiece is called the base metal, and the metal added to the joint from the electrode is called filler metal. Stick welding always adds filler metal to the joint. Because the electrode is constantly melting away and becoming part of the welded structure, stick welding is known as a consumable electrode process. As the electrode is heated by the arc, some of the covering of the electrode releases protective gases that shield the weld and help stabilize the arc. The remaining covering melts and covers the molten weld pool with a protective slag layer. This slag layer protects and helps shape the weld as it solidifies, but it must be removed when the weld is cool. Since the gases generated by the flux covering are able to completely protect the molten weld, there is no need for other shielding equipment such as high-pressure gas cylinders, regulators, or hoses. Compared to other welding processes, stick welding equipment is often very simple. Sometimes the only controls on the machine are current and polarity. Many important welding variables come from how the person doing the welding positions and moves the electrode. For this reason, the quality of welds produced by this process depends greatly on operator skill. In stick welding, two insulated wires are connected to the welding machine. One lead goes to a clamp which is connected to the work. This is called the work lead. The other wire goes to an electrode holder. The uncovered or grip end of the electrode is placed into the electrode holder. The polarity of the welding setup refers to how the electricity flows from the machine to the workpiece and back. The current will either be AC or DC. In AC, or alternating current, the direction of the flow of the electricity changes directions many times every second. Direct current, or DC, is like the flow of electricity from a car battery. One lead is always positive and the other is always negative. DC can be set up CEN, or DC electrode negative, which is often called straight polarity. In DCEN, the electrode is connected to the negative terminal and the work is connected to the positive. The other way to connect DC is DCEP, which is DC electrode positive, often called reverse polarity. Many stick welding electrodes operate on DCEP, but some are designed to work with DCEN or AC, so check the manufacturer's recommendations for the proper settings. Stick electrodes are made with a variety of metal alloy compositions and flux chemistries. You'll want to make sure the electrode you plan to use will be strong enough and that it's compatible with the base metal and the position of the joint you want to weld. Often, electrodes have the American Welding Society classification code printed on them. This code will identify tensile strength, the flux covering type, the appropriate welding positions, and sometimes other important information. So, in summary, stick welding is an electric arc welding process. It uses a consumable electrode rod that is covered with a flux material. When heated, the flux releases shielding gases that protect the weld. A layer of slag covers the weld while it solidifies and is removed when the metal cools. Stick electrodes are not all the same and must be chosen for the specific job they need to do.
All right, okay. So just now, wait, am I on? Okay. Okay, so just now we saw a video on shielded metal arc welding. So basically shielded metal arc welding, all right, the stick welding, is performed by a human welder. And as mentioned earlier in the video, it provides inconsistencies in the welding processes. So the applications of SMAL, used for steel, stainless steel, cast irons, and certain types of non-ferrous alloys. Not used or rarely used for aluminum and its alloy copper, and its alloys, copper alloys, and titanium. Okay, the next one we come to will be gas metal arc welding. Okay. So what this does is it uses a consumable bare metal wire as the electrode, right, with shielding by flooding arc with a gas. Wire is fed continuously and automatically from a spool, okay, through the welding gun. So basically now the wire is the consumable bare metal. Shielding gases include, okay, these are the gases, okay, which is used to create a shield: argon, helium for aluminum welding, and CO2 for steel. So bare electrode wire plus shielded gas eliminates slack on the weld bit. Okay, so there's no need for manual grinding or removal of the cleaning slack, which is produced in SMAL. So you can see this is the schematic diagram. We'll go straight to the video. Advantages of GMAL over SMAL. The better arc time because of continuous wire electrode. Stick must be periodically changed in SMAL, right? So in this case, because it's fed from a spool. Better use of electrode filler, better than SMAL. End of stick cannot be used in SMAL. So once it reaches a certain end, then you have to like throw it away. Higher deposition rates. You don't need to remove the slag, and it can be readily automated. Okay. So the electrode has a wire, all right, being fed, and the arc created. Sorry, to actually give you gas, metal, arc, welding, animation.
Polarity, wire speed, and voltage is the negative, and one is all. In MIG welding, a thin wire acts as the electrode. This wire is fed from a spool mounted on a gun or inside the welding
Sorry,
machine
just not on the
through
wrong
a flexible
video.
tube, and MIG stands for metal in. MIG stands for metal
So
inert gas
GMAL
welding.
is also
The
known
American
as
Welding
MIG.
Society calls this process gas metal arc welding, or GMAW. You might also hear it called wire welding. In MIG welding, a thin wire acts as the electrode. This wire is fed from a spool mounted on a gun or inside the welding machine through a flexible tube and out of the nozzle on the welding gun or torch. The wire is fed continuously when the trigger on the welding gun is pulled. When this trigger is pulled, it also switches on the welding current and a shielding gas. An electric arc forms between this wire electrode and the workpiece and heats both metals above their melting point. These metals mix together or coalesce and solidify to join the workpieces into a single piece. The metal in these parts to be joined is called the base metal, and the metal that comes from the melting wire electrode is called filler metal. MIG welding always adds filler metal to the joint. Because the wire electrode melts as it's being used, MIG is called a consumable electrode process. Here's the MIG wire going through the wire feeder into a flexible tube or conduit liner. The liner goes through the hose or welding lead all the way to the torch nozzle. At the nozzle, the wire is fed through a contact tip and comes out at the point of the weld. Shielding gas is also fed through the welding lead. It goes through a gas diffuser and flows out of the nozzle. This shielding gas, which is often a mix of argon and CO2, protects the molten metal from reacting with oxygen, water vapor, and other things in the atmosphere. The shielding gas is stored in high-pressure cylinders like these. The pressure is reduced to a usable level by a device called a regulator. In MIG welding, all the machine controls are set on the machine itself. Most important of these are polarity, wire speed, and voltage. The trigger on the gun is just an on-off switch. For most MIG welding, the current is direct current, or DC, coming from a car battery. One wire is all with MIG welding. CEP is used if turned. In an electric, back to the machine. In summary, MIG welding is an electric arc welding process. It uses a consumable wire electrode. Filler metal is added automatically, and the shielding gas comes from a high-pressure cylinder.
All right, let me just correct the website and okay. So now the next process is flux core arc welding. So what is FCAW? Adaptation of shielded metal arc welding. Okay, it's an adaptation of SMAL to overcome limitations of stick electrodes. Okay, so there are two versions. We have self-shielded FCAW and gas-shielded FCAW. So the first one, the core includes compounds that produce shielding gas, and the second one, it uses external applied shielding gases. So electrode is a continuous consumable tubing and coils containing flux and other ingredients. So this is the schematic diagram. Okay. Straight to the video.
Immunity is important for your child's learning potential. MFGM complex and DHA with key nutrients helps.
What is flux core welding? Flux core is an arc welding process that uses a tubular wire electrode with a flux-filled inner core. The American Welding Society calls this process flux core arc welding, or FCAW. All flux core welding is done on equipment that is similar to, and sometimes identical to, the equipment used in MIG or gas metal arc welding. If you're not familiar with MIG welding, you might want to watch our What is MIG Welding video before continuing. But you should understand that flux core welding has some important differences from MIG welding. In flux core welding, the wire electrode is fed through a wire feed unit. Usually, this wire feeder requires knurled rollers that can grip the tubular wire without flattening or damaging it. As in MIG welding, an electric arc forms between this wire electrode and the workpiece. This arc heats both metals above their melting point. These metals mix together or coalesce and solidify to join the workpieces into a single piece. The metal in the parts to be joined is called the base metal, and the metal that comes from the melting wire electrode is called filler metal. Because the wire electrode melts, flux core is called a consumable electrode process. Flux core welding always adds filler metal to the joint. The job of the flux inside the electrode depends on which type of flux core process it was designed for. You see, there are two main types of flux core arc welding: self-shielded, known as FCAWS, and gas-shielded, known as FCAWG. You need to be sure you're using the wire in the way that it was designed to be used, because the chemistry behind these two processes is different. Flux-cored electrodes that are designed to be self-shielded contain a flux that completely protects the molten weld pool. The flux in these electrodes creates a protective cloud that prevents gases like nitrogen and oxygen from reacting with the hot metal. One advantage of the self-shielded flux core process is that the added cost and inconvenience of gas shielding equipment is eliminated. Also, self-shielded electrodes are less sensitive to drafts and breezes that easily contaminate gas-shielded processes like MIG welding. This can be a real advantage in some applications. Electrodes designed to be gas shielded rely on a secondary shielding gas to do the job of protecting the molten weld. The high-pressure gas cylinders used for this process are of the same design as those used in MIG or TIG welding. These cylinders contain gas under extremely usable pressure. CO2-argon blends are also used to shield the weld. Another benefit of gas-shielded flux core is the high deposition rate that can be achieved with the combination of flux and gas. Gas-shielded flux core has the ability to lay down metal at an extremely fast rate. In both the self-shielded and gas-shielded processes, the flux forms a thin layer of slag that protects the weld as it cools. This slag also helps the solidifying weld to take a consistent low-profile shape. In flux core welding, all of the machine controls are set on the machine. Current flowing from a car used for this is positive. This is also called current flows in a loop. In flux core welding, the current has to flow in a complete circle from the machine to the gun, into the work and back to the machine. A work lead is clamped to the work to complete the circuit from the workpiece back to the machine. So in summary, flux core is an electric arc welding process. It uses a consumable tubular wire electrode that contains flux material on the inside. Filler material is added to the weld automatically as the wire electrode melts. In self-shielded flux core, the weld is protected by the flux itself. And in gas-shielded flux core, the shielding gas comes from a high-pressure cylinder.
Right, okay, so that would have been a clear enough video. Okay, the next one is electro-gas welding. So this uses a continuous consumable electrode, all right, a flux-cord wire, which like was there in the previous procedure, or a bare wire, with externally supplied shielding gases, molding shoes to contain molten metal. Okay. When flux core electrode wire is used and no external gases are supplied, then the case will be self-shielded, and it will be otherwise when the when the gases are supplied. All right. When a bare electrode wire used, all right, with shielding gases from external source, then it's a special case of dreamer. So the electro-gas welding, okay, uses flux core wire, all right, in a molding shoe. So basically, in this case, there is like a clamping process.
Hello guys, today we are going to discuss electro-gas welding.
So you can actually look through this video by yourself later. Okay,
Slag
it's a
is the
full
covering
explanation
material
on
or shielding material in electro-gas
electro-gas
welding,
welding. Let me bring
CO2,
you to.
you can see.
Okay. So this is also the schematic setup. Basically, the welding is done between a clamping of a what we call the molding shoes over here. Okay. So with the molding shoes, it provides like what we call a protection, and the welding pool is stabilized as well over here. Okay. So I'm not going to go through this because it's a long video basically giving the full explanation. Then we come into submerged arc welding. Uses a continuous consumable bare wire electrode with arc shielding by a cover of granular flux. All right, so this uses granular flux. So electrode wire is fed automatically from a coil. So flux introduced into joint slightly ahead of the arc by gravity from a hopper. So you pour in some granular flux ahead of the welding process. Completely submerges the operation underneath the flux. It prevents sparks, spatter, and radiation.
That's right. Every journey must start somewhere. What follow are the
now you have copper, which treats the granular flux. Okay, so that was submerged arc welding. Basically, it uses the arc welding process. And right now, what happens is the flux is poured in as a granule externally. Okay, the schematic diagram. All right. The applications, steel fabrication of structural shapes. So basically, when we want to weld I-beams and others in structure, civil environment, civil engineering environment, all right, we use the submerged arc welding. Seams for large diameter pipes, tanks, very, very huge structures, pressure vessels, all right? So, and components for heavy machinery, okay? And it's applicable for most steels except high carbon steels, and it's not recommended for non-ferrous metal. And then now we come to the non-consumable electrode process. Early on were all the consumable electrode process, and under which we have all this, okay? So moving to gas tungsten arc welding, it's a non-consumable process, a non-consumable tungsten electrode, and an inert gas for arc shielding, okay? So the melting point of tungsten is this, 3410. It's also called thick welding, all right, because of tungsten gas. So this is used with or without a filler metal. When the filler metal is used, it is added to a weld pool from a separate rod or wire. So the applications are usually for aluminum and stainless steel mostly. So this is basically the schematic diagram. The advantages, high quality of welds for suitable application, no spatter because no filler metal through arc. Little or no post-welding cleaning because there is no flux. So whenever there is a usage of flux in all our consumable rod, the formation of slag is usually present. Generally, it's slower and more costly than the non-consumable electrode method.
Nurture your child's potential to think quick and learn fast. S26 Gold Progress.
Gas tungsten arc gas welding. It is an arc welding process that uses a non-consumable tungsten electrode to produce the weld. The weld area is protected from atmospheric contamination by a shielding gas, usually an inert gas such as argon, and a filler metal is normally used, though some welds, known as autogenous welds, do not require it. A constant current welding power supply produces energy which is conducted across the arc through a column of highly ionized gas and metal vapors known as a plasma. Manual gas tungsten arc welding is often considered the most difficult of all the welding processes commonly used in industry. The reason is because the welder must maintain a short arc length, great care and skill to prevent contact between the electrode and the workpiece. Gas tungsten arc welding normally requires two hands, since most applications require that the welder manually feed a filler metal into the weld area with one hand while manipulating the welding torch in the other. However, some welds combining thin materials, known as autogenous or fusion welds, can be accomplished without filler metal. Most notable examples being edge, corner, and butt joints. To strike the welding arc, a high-frequency generator, similar to a Tesla coil, provides an electric spark. This spark is a conductive path for the welding current through the shielding gas and allows the arc to be initiated while the electrode and the workpiece are separated, typically about 1.5 to 3 millimeters, that is somewhere around 0.06 to 0.12 inches apart. Once the arc is struck, the welder moves the torch in a small circle to create a welding pool, the size of which depends on the size of the electrode and the amount of current. While maintaining a constant separation between the electrode and the workpiece,
Okay, so these are the details
slightly.
of the process.
After that, moving the torch forward, that is, to
What I
advance
want
the
you all to
weld pool
appreciate over here
and
is you
adding
can
filler
imagine
metal.
now it's going to be the
filler rod is
operator,
withdrawn
right?
from the
Who's got to
weld pool
control
each
both
time
the
the
arc as
electrode
well as the filler
advances,
material. So
but
that
it is
you
never
get a lot
removed
of
from the gas shield to prevent oxidation. Filler rods composed of metals with low melting temperature, such as the weld puddle. As the weld nears completion, the arc current is often gradually reduced to allow the weld crater to solidify and prevent the formation of crater cracks at the end of the weld.
So that is gas tungsten arc welding. And then now we move into plasma arc welding. All right. So this is a special form of gas tungsten arc welding in which a concentrated plasma arc is directed at the weld area. So tungsten electrode is contained in a nozzle that focuses high velocity of stream of inert gas, argon, into an arc region to form a high velocity, intensely hot plasma arc stream. Okay, so you can see the temperature over here. All right, it's unimaginably high. Due to constriction, all right, the temperature reaches this height due to the constriction of arc, producing a plasma jet of small diameter and very high energy density. Okay, so you have your tungsten electrode, your plasma arc, okay, and the shielding gas as it travels. Advantages of plasma arc: good arc stability and excellent weld quality. You get better penetration, naturally due to the temperature. You can move faster because of the better penetration. Can be used to weld almost any metals. The disadvantage: the equipment cost is very high and larger torch size than other arc welding processes.
In plasma arc welding, metal coalescence is produced by a constricted arc made up of a high-velocity stream of ionized gas called a plasma. In most plasma arc welding operations, the plasma jet is generated by heating the orifice gas in the torch polenum chamber to a plasma and forcing the plasma to exit through a constricting nozzle or orifice. Partial shielding is obtained from the plasma and is supplemented by an auxiliary shielding gas. Auxiliary shielding gases used include argon, helium, or mixtures of argon with hydrogen or helium. Because of the constricted arc, the heat energy of the plasma stream is concentrated and extremely intense. This permits deep penetration, narrow welds, and rapid welding speeds with good arc stability. Workpieces can be joined with or without filler metal. Plasma arc welding can be used to join most ferrous and non-ferrous metals, including extremely thin materials such as foils. Plasma arc welding equipment cost is high, however, so the process is often limited in its application.
Okay. And the next process is resistance welding. Okay. So again, now we are using non-consumable electrode, okay? So this is a group of fusion welding process that use a combination of heat and pressure to accomplish the coalescence. Heat generated by electrical resistance to current flow at the junction to be welded. Principle of resistance welding process is the resistance spot welding, okay? So you have, okay, I'll skip this video and I'll go straight to resistance spot welding, okay? So resistance welding, showing components in a resistance spot welding, okay? This is whereby, all right, parts to be welded are usually sheet metal, and we have two opposing electrodes, all right, to create the coalescence. The means of applying pressure to squeeze the parts between the electrode must also be there, and power supply from which a controlled current can be applied for a specific duration of time.
The new Enfagrow A+ Mind Pro, now with an improved formula.
So you see you have two workpieces put together. And we have two copper electrodes for the current will pass. So you can see the application of spot welding, all right? When you want to have this kind of fixtures, you can actually just, you can see, infuse the area. All right, and it is very much applicable in the automotive industry, frameworks, all right? When we just want to coalesce two parts together, just, you know, attach them like as if it's gluing, but it's actually welded. Okay. The advantages and drawbacks, all right? The pros, no filler metal required, higher production rates possible. It is very easy to automate, all right, and mechanize this process. Lends itself to mechanization and automation, lower operator skill level, all right, compared to all the arc welding processes we saw. And it's good repeatability and reliability. As I said, it is an automated process. Disadvantage, high initial equipment cost. We need to have the equipment set up, all right? It basically needs mechanization, all right? And limited to lap joints for most resistant welding process. So the joint should be an overlapping one, right? It cannot be a meet joint, okay? So the resistance welding process, okay, in which fusion of faying surfaces of a lap joint is achieved at one location by opposing electrodes, okay? So widely used in mass productions of automobiles, metal furniture, appliances, as we saw, all right? It says typically a car body has approximately 10,000 spot welds. So you can imagine annual production of automobiles in the world is measured in tens of millions of units, okay? So this is the spot welding cycle basically, all right? No electrode contact, and then you have the force, okay, which is increasing, okay, and then the force is maintained, and then the current is infused, okay, and the force is maintained. That means as the weld nugget is molten metal turns into weld nugget, the force is maintained, but the current is brought down, okay? So here the current is introduced, and then the current is brought down, and then the force is released. That means the electrode is released, okay? Force reduced. So this is the flow. And then we have resistance seam welding, all right? It uses rotating wheel electrodes to produce a series of overlapping spot welds along lap joints, okay? So this can produce airtight joints. The application would be tanks, automobile mufflers, all right? Various sheet metal containers, So this is the schematic diagram of the resistance spot welding. So if you remember the rolling process last time, all right? So something like that, but right now it is with electrodes, okay, and current involved. So you can see now you have an overlapping joint over here. So the brewery tank, containers, the exchangers, okay, material components. So these are all examples, all right, of resistance seam welding, okay. And then next we have resistance projection welding, all right. A resistant welding process in which coalescence occurs at one or more small contact points on the part. Contact points is determined by design of the parts to be joined. So this may consist of projections, embossment, or localized intersection of the part, okay. So you can see now the schematic diagram. Okay. Contact between parts is at projections, all right. When the current is applied, the weld nuggets, similar to spot welding, they will form. So wherever there is an embossment or projections, okay, we expect the weld nugget to form in those areas. So you see it's actually in a single contact area. This is almost a tangential contact. So the projection either collapses and creates the fusion, or it is a tip-to-tip joint actually. So all the cross wiring uses projection welding. You can also use part component, right? Okay. And then we have other resistance projection welding operations like we saw earlier on, right? On fasteners, cross wires, okay? And then we come into oxy-fuel gas welding, all right? So it's a group of fusion welding operation that burn various fuels mixed with oxygen, all right? So we are using gas, okay? Oxy-fuel employs several types of gases, which is the primary distinction amongst the members of this group, all right? So oxy-fuel gas is also used in flame cutting torches to cut and separate metal plates and other parts, okay? So not only does this do welding, it does cutting as well. So the most important factor of the oxy-fuel process is the oxyacetylene welding, all right? So it's basically using oxyacetylene and oxygen, all right? The flame is directed by a welding torch. Filler material is sometimes added. Okay, so composition must be similar to base metal, the usual thing. Filler rod, often coated with flux, is also present, all right, to clean surfaces and prevent oxidization. Okay, so here what is different is what is being channeled in, right? It's a mixture of oxyacetylene. Okay, and then you have your filler rod, which is externally imparted, all right? So acetylene is the most popular fuel among OFW group because it's capable of higher temperatures than any other. And it has a two-stage reaction. The first one, all right, gives you the inner cone flame, and the second one, the outer envelope. Okay.
Of 40 to 50 degree.
Introducing Centrum Energy, the secret for sustained energy and all-day mental clarity. Centrum Energy.
Nivea Hokkaido Rose with Foam, enriched with 36 times antioxidant to restore skin's radiance for rosy and healthy skin.
Used in oxyacetylene welding. Oxyacetylene welding equipments are as follows: regulator, oxygen control valve, acetylene control valve, oxygen cylinder, acetylene cylinder, hose, welding torch. These are all the equipments are commonly used in oxyacetylene welding. Oxygen cylinder. We are going to see the specification of oxygen cylinder. This is the 3D view of oxygen cylinder. The standard color for the oxygen cylinder is black. The oxygen cylinders are usually filled at a pressure of 80.
I will not go into the details of how the gases are stored.
Now we take a close look of acetylene cylinder valve. Acetylene cylinder is made of steel. Valve fitted to pressure regulator.
What happened?
Working of fuel gas and oxyacetylene in correct proportions and burning the mixture at the end of a tip, which produces a high temperature flame.
Flame over here.
Forward or leftward welding. Let us see the forward and leftward welding. This welding consists of filler rod, welding torch. In this method, the welding torch is held in the operator's right hand side and the welding rod in the left hand side. Welding direction. In this welding, the torch flame moves from right to left. Filler rod makes an angle of 30 to 40 degree. Torch makes an angle of 60 to 70 degree. This technique is suitable for MS plates up to 5 mm thick and also used for cast iron and non-ferrous metals. Backward or rightward welding. The backward welding is one of the gas welding technique. This welding consists of filler rod, welding torch. Welding action starts at the left hand side and proceeds to the right hand side. Welding direction. In this welding, the torch flame moves from left to right. Filler rod is held in the left hand at an angle of 30 to 40 degree. The torch is held in the right hand at an angle of 40 to 50 degree. This method is better and economical for plates over 6 mm thickness. Vertical welding. This welding consists of filler rod ahead followed by the blow.
So you can use the same concepts, all right, in vertical.
Now we are going to see a visual representation of gas welding. Accessories and its uses. The gas welding accessories are as follows. Wire brush. It is used to clean the surface of the joint.
Alright, so I'll skip this so you can look through. So basically that's the gist of oxyacetylene welding. Okay. And then here, this video here speaks about the
types of flames. First one is neutral or oxidizing flame. Approximately equal volumes of oxygen and acetylene are mixed in the welding torch and burnt at the torch tip. The temperature of the neutral flame is of the order of about 5900 degree Fahrenheit or 3260 degree centigrade. The flame has a nicely defined inner cone which is light blue in color. It is surrounded by an outer flame envelope produced by the combination of oxygen in the air and superheated carbon monoxide and hydrogen gas of will be a carburizing flame or reducing flame, much brighter in color. Carburizing flame is used, it ensures the absence of oxidizing condition. Next, oxidizing flame.
Okay, and then we have the final one, which is the oxidizing flame. All right, so you can look through the video, all right, to see the nature of these flames. The maximum temperature reached at the tip of the inner cone, okay, is 3480 Celsius, while the outer envelope is, of course, much lower, all right, and spreads out and shields work from surface, from atmosphere, okay. So the safety issue, acetylene and oxygen, they are highly flammable, and this is a colorless and odorless gas, all right. It is therefore processed to have characteristic garlic odor so that we can actually identify, all right, the presence of the gas. So acetylene is physically unstable at pressures above, all right, 1 atmospheric pressure. So storage cylinders are packed with porous filler material saturated with acetone. Acetone dissolves about 25 times its own volume of acetylene, all right. Different screw threads are standard, all right, on this acetylene and oxygen cylinders, all right, in order to contain the gas carefully. So the alternative gases for acetylene, oxyacetylene, all right, we have methyl acetylene propadiene, hydrogen, propylene, propane, and natural gases, okay. Now we come to other fusion welding processes, okay, that cannot be classified under arc welding, resistant welding, or using any kind of fuel, all right, welding. So use technologies to develop heat for melting, all right, and the procedures under this would be electron beam, laser beam, electrostatic, and thermit, okay. So the electron beam welding, fusion welding process in which heat for welding is provided by a highly focused high intensity stream of electrons, okay, striking the work surface. So the electro beam gun operates at high voltage, all right, from 10 to 150 kilovolts to accelerate the electrons. The beam currents are low, okay. The power in electron beam welding is not exceptional. The power density is, okay. So if you look at the video.
The new Enfagrow A Plus Mind Pro, now with an improved formula.
Welcome to Academic Game Tutorials. This will be update tire process. This electron generating cathode to bore electron gun is mostly made by tungsten or tantalum alloys. Now, when power supply is provided to this negative charged cathode tube, the cathode filament is heated and generates electrons. The cathode filament is heated up to 2500 degrees centigrade for continuous emission of electrons. Now, when electrons have been generated, we need to increase the velocity of electrons for the welding process. For increasing the velocity and accelerating the electrons, we need to create a potential difference between this cathode and an anode. So, here we have an anode, which is a positive terminal. When power supply is given to the anode and the cathode, then a potential difference of around 30 kilovolts to 175 kilovolts is created between this anode and cathode. Due to the potential difference created between these two terminals, the anode accelerates the electrons coming from the cathode and forms an electron jet. So, this anode is a positive pole which is just after the electron gun. Its main function is to attract negative charged electrons generated from the cathode, accelerate these electrons and provide them a path so that they do not diverge away and can be focused together in towards the next components. Now this accelerated and high-velocity electron jet will go past the anode and reaches the focusing coil or focusing lens placed here. When electrons are coming through all this way from the cathode and passing through anode, with increasing distance from the source, these high-velocity. Now, just like a convex lens or converging lens which concentrates or focuses all the entering dispersed light rays to one point. Almost similarly, here we have a focusing coil or focusing lens that prevents the incoming high velocity. Here we have a deflecting coil. This deflecting coil deflects the beam at required weld area on the workpiece where we need the welding joint to take place. Here, we have the workpiece or the parts that are to be joined. There is a fixture down here on which the workpiece is fixed firmly so that it does not move during the welding operation. This welding operation takes place inside a vacuum chamber. The workpiece fixed on the fixture is placed inside this vacuum chamber. When this deflecting coil deflects the beam, this high-velocity accelerated electron jet enters this vacuum chamber and concentrates on the point where the beam is deflected to create welding on workpiece. What actually happens at this point on workpiece is that, when highly accelerated electrons with kinetic energy will concentrate and hit on this point of the workpiece, then the kinetic energy of these electrons will convert to thermal energy and produce heat. This heat will fuse and melt the metal workpieces and create a joint or welding between them. This vacuum chamber is created surrounding the place of welding, so that the electrons do not come in contact with air, and we can utilize the maximum penetrating power of these electrons. Welding would take pulse even if this vacuum chamber was not created, but in that case these deflected electrons would come in contact with the air and deviate in some proportion, instead of getting a concentrate, and we wouldn't get. It is not possible to.
This is basically the principle for electron beam welding, and very clearly, systematically explained over here. Okay. And as mentioned earlier, there was the electron beam vacuum chamber. All right. So when this was first developed, it had to be carried out in a vacuum chamber to minimize disruption of electron beam by air molecules. All right. So this is a serious inconvenience in the production, and it can take a downtime. All right. Three vacuum levels in the electron beam welding. We have high vacuum welding, welding in same vacuum chamber as beam generation to produce the best quality. Medium vacuum welding in separate chamber, but partial vacuum reduces pump downtime. Non-vacuum welding, welding done at or near atmospheric pressure with work position close to electron beam generator. So this requires vacuum divider to separate work from the beam generator. Pros and cons. Pros: high quality welds, deep and narrow profiles, limited heat affected zones, okay, due to the nature of the weld itself, all right, and weld tool, okay. Low thermal distortion, no flux or shielding gases needed. Disadvantage, of course, equipment cost is very high. Precise joint preparation and alignment required, and you need a vacuum chamber, okay. And then there are safety concerns because electron beam welding generates X-rays. Okay, the next process is laser beam welding, all right. Fusion welding process in which coalescence is achieved by an energy of a highly concentrated coherent light, all right, laser, okay, beam focused on joint. So this is normally performed with shielding gases to prevent oxidization. Filler metal is usually not added. High power density in small areas. So we look at this. the tensile test done, all right? The laser beam strength, and then mechanical, compressive tests, all right? Cutting to see the strength of the laser beam. Okay, so when we compare LBW and EBW, for laser beam, no vacuum chamber required, no X-rays emitted. Laser beam can be focused and directed by optical lenses and mirrors. Laser beam not capable of deep welds and high depth to width ratios of electron beam welding. Okay, so it has a range of depth, right, about 3/4 inches, whereas electron beam can go into up to 2 inches in formation. And then we have thermit welding, all right. It's a fusion welding process in which heat for coalescence is produced by superheated molten metal from the chemical reaction of thermit, all right. Thermite, mixture of aluminium and ferrous oxide, all right. Fine powders that produce an exothermic reaction when ignited. Also used for incendiary bombs, okay. So the filler metal obtained is from the liquid metal. The process used for joining but has more in common with casting than welding, actually speaking, okay. So thermite, over here you have the schematic diagram, all right. Thermite is ignited, okay. The crucible is taped, superheated metal flows into the mold, and metal solidifies to produce weld joint. So you see you have your part over here, okay, and then you have the mold to hold. You have a heated molten metal which is just poured in pretty much to actually solidify, and then you have your slag which you take out. So it is as why they say casting, because it's like, you know, pouring in a molten metal to actually fuse two parts together. Okay. So joining of railroads, the application, repair of cracks in large steel casting and forging. Weld surface is often smooth enough that no finishing is required, because basically if we're dealing with molten metal. I'm going to skip the video for this. Okay. And then we come into solid state welding. Okay. Coalescence of part surface is achieved by pressure alone or heat and pressure. Okay. So earlier on was fusion welding, everything that we saw. Now it comes to the second part, which is solid state welding. Okay. If both heat and pressure are used, heat is not enough to melt the workpiece surfaces. So for some solid state processes, time is also a factor. So no filler metal is added. Each solid state process has its own way of creating a bond at the faying surface, the meeting surface. Essential factors for a successful solid state weld are the two faying surfaces, which must be clean, no contaminant, in very close physical contact with each other to permit atomic bonding. Okay. The advantage of a solid state compared to fusion welding is no melting. Then there will be no heat affected zone, or we call HAZ. All right. So metal around joint retains its original property. Many of this process, all right, solid state process, produce welded joints that bond the entire contact interface between two parts rather than at distinct spots. So some solid state processes can be used to bond dissimilar metals, all right, without concern about relative melting points. So two different metals can be actually bonded. And then you don't need to be worried about melting points, thermal expansion, and other problems which come about in fusion welding. So these are all the processes within a solid state welding. Okay, so we have forge welding, the process in which components to be joined are heated to hot working temperatures range, then forged together by hammering. So this is basically like a forging where blacksmiths used to do those days. So you can see both parts are right heated up and then hammered together, basically, so that they will fuse with each other. Okay, so this part is forge welding. All right, and then we have cold welding. All right, it's a process done by applying high pressure between clean contact surfaces at room temperature. Cleaning usually done by degreasing and wire brushing, okay, before joining. No heat is applied, but deformation raises work temperature. At least one of the metals, preferably both, must be ductile for this to happen. So soft metals like aluminium and copper suited to this process.
Cold or contact welding is a solid-state welding process in which joining takes place without fusion heating at the interface of the two parts to be welded. Unlike in the fusion welding processes, no liquid or molten phase is present in the joint. Metal would strongly adhere if broad fabrication processes. The reason for this unexpected behavior is that when the atoms in contact are all of the same kind, there is no way for the atoms to know that they are in different pieces of copper. When there are other atoms, in the oxides and greases and more complicated thin surface layers of contaminants in between, the atoms are when they are not on the same. This allows the broadly defined notions of galling, fretting, sticking, stiction and adhesion to overlap in some instances. Fast surface.
So basically it allows the atomic bonding to take place to fuse.
What is TIG welding?
Sorry.
TIG's
or contact welding is a solid-state welding process in which joining takes place without fusion or heating at the interface of two parts to be welded. Unlike the fusion welding process, no liquid or molten phase is present in the joint. Cold welding in the 1940s.
So it's basically like putting plasticine together, but it's just that this is metal. Huh?
Newly discovered micro and nanoscale cold welding has already shown great potential in the latest nanofabrication processes. The reason for this unexpected behavior is that when the atoms in contact are all of the same kind, there is no way for the It's been said the phenomenon of two pieces of metal would not normally fuse just by touching, even in space. You need to get two perfectly smooth corrosion-free surfaces of similar metal, usually stainless steel, and press them together with some force to get them to fuse into one piece, as in the process of cold welding. You need two atomistically smooth surfaces of the same material with the same orientation, uncontaminated by any impurities or surface defects for vacuum fusion to take place.
Okay, so that's for cold welding. And then we have roll welding. Okay, so this is a process in which pressure should be sufficient to cause coalescence. All right, is applied by means of rolls, either with or without external heats. So this is a variation of either forge welding or cold welding, depending on whether heat of work part is done prior to process. If no heat, then it's cold roll welding. If heat is applied, then it's hot roll welding. So basically, it is like rolling, where two plates are put together, and then the force causes the plates to be bonded. Okay, so cladding stainless steel to mild or low alloy steel for corrosion resistance. So bimetallic strips for measuring temperature, okay, also goes through this process. This is somewhat similar to the seam welding process. Okay, so here the process used will be like the sandwiching, all right, for coins for the US minting. Okay, and then we have diffusion welding. This process uses heat and pressure, usually in a controlled atmosphere with sufficient time for diffusion and coalescence. All right, so the temperature should be less than half of the melting temperature. All right, so plastic deformation at surfaces is minimal. The primary coalescence mechanism is solid state diffusion. The limitation for this process, time required for diffusion, can range from seconds to hours. So the application, joining high strength and refractory metals in aerospace nuclear industry, can be used to join either similar or dissimilar metals. All right, for joining dissimilar metals, a filler layer of different metal is often sandwiched between the base metal to promote diffusion. this is the inner atomic behavior, right, in diffusion welding. Okay, so the parts have become one like that. And then you go on to explosion welding. Okay, so it's a solid state process in which rapid coalescence of two metallic surface is caused by the energy of a detonated explosive. So here no filler metal is used, no external heat is applied, no diffusion occurs because the time is very short. Bonding is metallurgical combined with mechanical interlocking that results from a rippled or wavy interface between metal. So this is commonly used to bond two dissimilar metals, okay? In particular, to clad one metal on top of a base metal over large areas, basically to put one metal on top of another, okay? The setup you can see in config 1 and 2. So you have your detonator, right? And then you have your explosive. And then there is a buffer, and there's a flyer plate and the backup plate, all right? This is the clearance gap, okay? So when the explosion happens, all right, the formation of the plate takes place, okay? Formation of the welding, bonding takes place.
Explosion welding is one of the joining methods consisting of a solid-state welding process in which controlled explosive detonation on the surface of metal surfaces. Flare plate or cladder collides with the base plate, resulting in a bonding at the interface of the metals. The metal plates are joined at an internal point under the influence of a very high pressure and causes considerable local plastic deformation at the interface, in which metallurgical bonding occurs in nature and even over here. One of the features of this welding process is that similar and dissimilar metals can be joined by this process. Diagram and working animation. This is a schematic arrangement for explosive welding. The main component in this welding process are: first one, this is parent metal or base plate. We put it on the anvil. Above it, we put a flare plate with some gap, which is called standoff distance. It is placed using guided pins to keep the uniform gap in between both the flare plate and parent metal. And right above it, we put some explosive uniformly. It is utterly important to decide and calculate the quantity of explosives and velocity of explosion. Later, detonation is started by using detonator switch, and it is also important to start detonation from one end of the cladder. Then the detonation moves upon the upper layer of cladder at the uniform speed, and this explosive front progressively drives cladder plate downward to the base plate at a very small collision angle caused by which forces the impurities and other oxide to get removed between the...
Okay, so basically what happened? I'm sorry, why did my PowerPoint close down?